What's up, my chem peeps? In this vid, we're going to explain the concept of isomerism in organic molecules. Two big things we're going to do. One, we're going to define and identify structural isomers of organic compounds. Two, we're going to define and identify geometric isomers of organic compounds. Okay, so the difficulty in depicting the Lewis structure of many organic compounds from their molecular formula is due to isomerism, or molecules having the same molecular formula but different structures. And so in general, when we talk about isomers, we're talking about different molecules with the same molecular formula. As an example, let's take a look at the molecular formula C4H10, the hydrocarbon known as butane. And this idea of having the same formula but completely different molecules is the idea behind isomerism. Now first, let's talk about structural isomers. These are isomers that have a different pattern of atom attachment. Again, let's take a look at the example of C4H10 and the two isomers that are on your screen, butane and isobutane. Notice that in butane, we've got a carbon chain that is 4 carbons long. But in isobutane, the longest carbon chain is 3 carbons. Doesn't matter how you count, the longest chain we can get is 3 carbons. Structural isomers. Same number and type of atoms, but a different pattern of attachment. Some important things to keep in mind. Because of their different structures, they have different properties. And it's important to know that you can no longer just rely on a molecular formula to show you the attachment pattern in the molecule, which is why it's often helpful to look at what's called the structural formula, which shows you not only the number of atoms, but the pattern of attachment as well. So take a look on your screen and in your notes. You're given some examples of structural formulas and condensed structural formulas and help you differentiate between the different types of isomers that you might be working with. Again, we're not going to dive into organic chemistry all that much, so I want you to just keep the following tips in the back of your mind. In general, the attached atoms are listed in order, so lean on your structural formula to help you understand how those atoms are bonded to one another. 2, follow the normal bonding patterns. Remember that carbon forms 4 bonds. Nitrogen, if you have it, forms 3. Oxygen, if you have it, forms 2. Fluorine and hydrogen each form 1. 3, keep in mind that sometimes you'll see parentheses, and these are simply used to indicate more than one identical group attached to the same previous central atom. And then finally, just realize it gets easier with practice. No shortcut. Just practice, practice, practice. All right, in addition to structural isomers, you're also going to encounter geometric isomers. And these are molecules in which the atoms have the same molecular formula and the same connectivity. So the same pattern of attachment, but a different spatial arrangement. Geometric isomers. Now, these are also known as cis-trans isomers and are distinguished from one another based on the relative position of 2 functional groups on the organic compound. We use the term cis to indicate the same side, so those functional groups will be on the same side of the organic molecule, and the term trans meaning opposite side, or the functional groups will be on the opposite sides of the organic molecule. So to help you understand this, let's look at an organic compound that contains 2 carbon atoms and 2 chlorine atoms as our functional groups. In the first example, notice that the carbon atoms are singly bonded together. In other words, they're attached with a sigma bond. And because it's a sigma bond, the molecule is able to freely rotate about that bond. And because it can readily sort of interconvert, we don't have geometric isomers here. So take a look at the image on the left. It shows the 2 carbon atoms singly bonded together. And the carbon atom is free to rotate about that single bond. However, you can have geometric or cis-trans isomerism if you have a double or a triple bond. Because remember, in a double or a triple bond, we do get some pi bonds involved. And the pi bonds restrict the rotation and gives us 2 distinct isomers. So once again, as an example, we've got an organic compound with 2 carbon atoms and 2 chlorines as our functional groups. Notice that if both of those chlorines are locked on the same side, we say that that's the cis version of that isomer. If they're locked on opposite sides, we call that the trans version of the isomer. So let's come back to this animation. The image on the right indicates a double bond between the 2 carbon atoms, one of those bonds being a pi bond, and it locks the carbon in place. It's not able to rotate, which allows for the creation of two distinct geometric isomers, something that we were not able to see when the carbon atoms were simply single bonded together and able to freely rotate. Now, why is this important? Why are we talking about this now? Recognize that the distinct isomers have distinct properties. The type of isomer that you're working with will determine the molecular polarity and therefore the types of intermolecular forces of attraction that you'll find between those different molecules. And notice how that can affect melting points or boiling points, for example. Alright, that does it for this vid. Have a fantastic day.